Good afternoon. Good evening. How's the sound? Can you hear me? Everyone hear me okay? Great. Well, good evening. I'm Rachel Bronson. I'm the Executive Director and Publisher of the Bulletin of the Atomic Scientists. And on behalf of the Bulletin and its partners, I'm delighted to welcome you to tonight's program with Lawrence Krauss on his new book, The Greatest Story Ever Told, so far, a story about reality and all of its messiness. Lawrence Krauss is a theoretical physicist and a cosmologist who is foundation professor of the School of Earth and Space Exploration at Arizona State University and the director of its Origins projects. He is known as an advocate of the public understanding of science, of public policy based on sound empirical data, of scientific skepticism, and of science education. Dr. Krauss is the author of several best-selling books, including The Physics of Star Trek and A Universe from Nothing, among other works. He is the recipient of many honors and a board member of the Federation of American Scientists. Lawrence is also the chairman of the Bulletin's Board of Sponsors, a group of leading scientists and security experts from around the world that includes 16 Nobel Prize winners who endorse the activities of the Bulletin of Atomic Scientists. As many of you know, the Bulletin is a 70-year-old organization located in Hyde Park, founded by Manhattan Project scientists who are concerned that the advancement of science and technology was fast outpacing our ability to manage it. In 1945, nuclear energy was the perfect example of what one of our founders called Pandora's box of modern science. And today's issues of climate change and emerging technologies like artificial intelligence and cybersecurity raise similar challenging questions. The Bulletin publishes a bi-monthly journal and hosts a very active website at www.thebulletin.org that tackles these topics daily. You may also know the Bulletin from our iconic Doomsday Clock that is set by our board of directors each year. Our board is in town tonight for its biannual meeting, which will be held tomorrow. Many are here tonight, and I'd like to offer them a particularly warm welcome. I'd like to take a moment to thank our partners for their help with tonight's program, the Chicago Council on Science and Technology and the Illinois Science Council. Many of you have heard about the program through our partners. The Chicago Council on Science and Technology, or C2ST, is celebrating 10 years as a not-for-profit organization. C2ST brings scientists out of the lab directly to the public. It works with national laboratories, leading academic institutions, and museums to educate the public on issues of critical scientific importance. In an age when barely 1 in 4 voting adults meet a basic level of scientific literacy, C2ST's aim is to reignite an excitement and passion for science and technology and remind Chicagoans of the quality and quantity of R&D that takes place in our own backyard. Thank you also, C2ST, this is quite important actually, C2ST has also made it possible to video tonight's program. If you miss a word tonight or would like to share tonight's program with friends, you'll be able to find that video on tonight's programs on C2ST's website in the Bulletin. So thank you to Christina Elicke and her entire team, many of whom are here with us tonight. Thank you also to the Illinois Science Council. ISC is an independent, volunteer-driven 501c3 organization that engages, educates, and entertains the adult public about science, technology, engineering, math, or STEM in everyday lives. It highlights the scientists and research of the Chicago area institutions and companies that make Chicago the nation's true city of sciences. Thank you to its executive director, Monica Metzler, for ISC's help in getting the word out for tonight's program and helping to ensure tonight's sellout crowd. After remarks from Dr. Krauss, I'll be back on stage to help moderate a Q&A with the audience so we can pick up on maybe where he left off. And after the program's copy of Lawrence's book and other of his bestsellers will be available, and he'll be available for signing. You probably passed them as you came in. I'm also delighted to share that tonight's program is being broadcasted live across the world via Facebook Live. So with that, please help me in welcoming to the stage Lawrence Krauss.
Thank you, Rachel. Thank you. Well, thank you. It's always an honor to do anything for the Bulletin. It's nice to be here to talk about this subject, which I want to concentrate on the part of the book that I think is most relevant to the Bulletin. So that's what I'm going to do. And if you want to read the rest or hear the rest, you have to read the book. More importantly, you have to buy the book. But But this is actually one of my favorite quotes. I was first brought to my attention by a friend of mine, a filmmaker named Werner Herzog, who loved this book, The Peregrine. It's a naturalist book. It's about a peregrine, and literally all about the peregrine. The person evaporates quickly at the beginning. But this quote, I think, is very important for what I want to talk about, the story that I told in this book. It's also, I think, important for the Bulletin. It really captures, in some sense, one of the things that I think the Bulletin, and see John over there, is so good about, which is to reveal to people the reality of what's really there, which should be the basis of public policy and too often isn't. And so I think it's particularly appropriate to use that quote here. But now here what I want to talk about is the amazing story of the illusion of reality that science has helped us uncover. It is amazing that the universe we see is literally an illusion in ways that I'll describe to you. And in fact, let me begin in this case by using this image, which I allude to in the book. So this is in Chicago. You know what these are, actually. I was speaking about this to a group in Phoenix a while ago, and they had no idea what they were. But anyway, these are ice crystals on a window, as you see in May in Chicago. So what I want you to do for a moment is imagine that you're on one of these crystals, say this one, and imagine that your civilization emerged and grew on that crystal. What would it be like? Well, there'd be something very special about that crystal, that direction there. And physicists would develop and understand laws of physics that would tell you that the forces along the spine of the crystal would be different than the forces perpendicular to the crystal. And they'd explain them and codify them and maybe even develop laws to describe them. And theologians would explain why this direction was meant by God. And wars would be fought, in fact, over whether it was this direction or that direction. That was the important one. And all of this would give a significance to something that has no significance whatsoever. And that's the key point. There's no significance to that direction at all. It's an accident of nature. And it could have been lived on any of these other crystals. What we have learned is that is exactly the case in our universe in ways that I want to describe to you, in ways that are remarkable. That the many things that we consider significant, that we consider designed for our existence in our universe are similar accidents of existence in a very real way. So the story, of course, in the book goes back to Plato and beyond, and goes through many of the key revolutions in this greatest story of humans being taken by nature to understand reality, whether they wanted to understand it that way or not, through Maxwell and Faraday and Einstein and the unifications of the 19th century of electricity and magnetism, two forces of nature that seem quite different, but really are seen as two manifestations of the same thing. The hallmark of progress in science is just that. Whenever two things which on the surface seem completely different are seen as exactly the same thing. At least in physics, that's certainly the hallmark. And that unification of electricity and magnetism led to a unification of space and time that Einstein realized. Einstein wouldn't have been Einstein if it hadn't been for Maxwell and Faraday. He would have been Einstein, but we wouldn't be talking about him if it hadn't been for Maxwell and Faraday. And relativity was the unification of two things which on the surface seem completely different, space and time. But in fact, one person's space is another person's time. And this beautiful edifice was built in the last part of the 19th century and the beginning of the 20th century. And then where I want to pick up on it now is where things had to change because of the discovery of quantum mechanics. So I want to pick it up with this guy here, who all of you recognize, or many of you do, Richard Feynman, who I wrote a book about, who worked on the Manhattan Project alongside many of the scientists who would later help found and lead the Bulletin and the board of sponsors. And Feynman was a remarkable scientist, one of the greatest scientists of the second half of the 20th century. But he assigned himself the task, and later did, along with several others for which he won the Nobel Prize, of reconciling this beautiful theory of electromagnetism that Maxwell and following Faraday had developed, this beautiful theory that described light, the existence of light, as an electromagnetic wave, and allowed all the phenomena that now make this room possible. But quantum mechanics had been discovered to describe nature on very small scales, and quantum mechanics is strange in the extreme. and Feynman and others tried to figure a way to reconcile electromagnetism and quantum mechanics, successfully eventually. And the key idea, the key craziness of quantum mechanics is that it's like, as I often say, it's like Washington or corporate America, which are now the same thing, in the sense that if you can't see it, anything goes. Okay? That's quantum mechanics. And we'll be learning more about that with investigations over the coming weeks. But the key point is that this is really a reflection of something called the Heisenberg uncertainty principle. The fact that if I measure a system for a short amount of time, then doesn't matter what kind of machine I have, it's independent of the machine I have. If I measure a system for a short period of time, then I can only know certain quantities approximately and not exactly. If I measure it for a certain amount of time, I can only know the energy of this system approximately. And there's no way I can know it exactly. Now, that point eventually allowed Feynman and others to develop a picture of the quantum theory of electromagnetism called quantum electrodynamics. And he developed it pictorially, as he did many things. This is what we call a Feynman diagram. And this is how we now understand the interaction of two electrons that repel each other, as described originally classically by others before Faraday and Maxwell, but eventually them as well. So here's an electron repelling another electron. We now understand it quantum mechanically as follows. The electron emits a particle, the quantum of the electromagnetic field. Electromagnetic waves are waves, but they come in particles, batches of particles called photons. And so the light coming into your eyes is individual photons that are being received. That's the quanta of the electromagnetic wave. Okay, so the electron emits a quantum called a photon. That is interesting, however, that's impossible. It can't happen in the real world because an electron just sitting there cannot emit a photon, because if it emitted a photon, the photon would carry away energy, but the electron would still be there, and where did the energy come from? There's no way you can, that just cannot happen. But this is quantum mechanics. If you can't see it, anything goes. So if the photon survives for such a short time that you can't measure the energy it carries away, then it's fine. It's just like embezzlement, in fact. It's identical to that. As long as you get it back in the morning, then you can do whatever you want with the money at night. And the photon in this case, so the photon is emitted, it's received by this electron, causing that repulsion. And we call this a virtual photon because it isn't there. If you could see it, you'd see the violation of energy. But you can't. But as long as it disappears in a time scale so short that you can't measure that energy violation, anything goes. And this picture describes exactly the electromagnetic interaction, producing the best theory we have in nature, the best theory we still have in nature. With this theory, from fundamental principles, you can explain and describe and predict the results of experiments on atomic systems at the level of 14 decimal places. The comparisons of the predictions and the observations, there's nowhere else in science that you can predict things to 14 decimal places. This is as good as it gets. It never gets better than this. And there's one other aspect of this interaction that's important. First, you emit the photon. It's a virtual particle. Transmit the interaction. But the other thing that's important about electromagnetism is it works across the universe. Vitally important for our existence. We can see stars. We can see the light from stars. But an electron here will repel an electron in Alpha Centauri 4 light years away, or in a different galaxy, because electromagnetism is a long-range force. Now, quantum mechanically, we understand that as follows. The photon is massless. Why is that the case? Well, E equals mc squared. And because the photon is massless, the photon can carry an arbitrarily small amount of energy when it's emitted. But if it can carry an arbitrarily small amount of energy, then it can travel for an arbitrarily long time without being detectable by violating the Heisenberg uncertainty principle. Because if the energy carried by the photon is so small, you can't measure that energy violation. So the photon can exist for an arbitrarily long amount of time. In fact, so long that it could travel from here to Alpha Centauri and be absorbed. So the reason electromagnetism is long range is because the particle that transmits that interaction is massless. So the Heisenberg uncertainty principle allows it to travel as long as it wants before it's absorbed again by carrying an ever small amount of energy. Okay, that's it. Now you understand quantum electrodynamics in principle. The rest is practice, your homework problems. They'll be handed out afterwards. Okay, so that's it. That's as good as it gets. Now we have a quantum theory of electromagnetism developed in the 1940s, completed after the interruption of science by the Second World War. The Interruption of Physics, brought together great physicists, but there was some interesting physics going on, but people like Feynman didn't do the real work till after the end of the war, and then produced the greatest theory we have. That's great, until nature intervened. And nature intervened by something that's relevant in this room and to the bulletin. A fact which should discourage some of you. The neutron is radioactive. This, I remember learning this from a wonderful astronomer named Tommy Gold when I was in high school. It shocked me. It should shock you too, because your body's made of neutrons. Most of the particles in your body are neutrons. There are more neutrons than any other particle in your body, because the atomic nuclei of atoms have protons and neutrons, but the heavier atoms have more neutrons than protons. So neutrons are the most abundant particles in your body. But if I take a neutron and hold it here, it will live 10 minutes, okay, before it decays. That's the lifetime of a neutron. Some of you will notice that you were listening to that song go on interminably for more than 10 minutes before the talk, and maybe you were hoping that your neutrons would decay. So the question is, what gives? How come you're here if neutrons have a lifetime of 10 minutes? How can you be here? How can any stable elements be here? Well, it's an interesting accident of nature. So the neutron decays into three particles, a proton, and this is a fancy way of writing an electron, and a neutrino. Three particles. Now, the amazing accident is that a neutron and a proton weigh almost exactly the same amount. The neutron is 1 part in 1,000 heavier than the proton, but the two are almost exactly the same mass. And now that means the neutron has barely enough mass to allow it to decay, because its mass is barely heavier than the sum of the mass of the proton plus the electron plus the neutrino. And because it can barely decay, it takes a long time to decay. Take 10 minutes, which doesn't sound long, but in particle physics units, that's a long time. And so we call that a weak decay, because it takes so long to happen. This weak interaction is a new interaction of nature, however, this complicated thing. Before that, we had gravity and electromagnetism. Gravity can't cause this. Electromagnetism can't cause this decay. So somehow there's a new force in nature that was discovered. And that force meant we had to describe it. This force is weak but important. It's one of the reasons we're here, two reasons. But let's first go into the reason we are here, the reason the nuclei in your body exist. So the neutron decays in 10 minutes, if I have it out here. Now let me drop it in a nucleus. What happens when it gets dropped in a nucleus? It gets bound. What does it mean to be bound? Well, some people know. But what does it mean to really be bound? It means it takes energy to get out. I'm bound to the earth. So when I jump down off the stage, walking down because I don't feel like jumping, it takes energy to get back up. Okay? So I lose energy when I get bound to a system. So the neutron loses energy here, but E equals mc squared. So the neutron loses energy, and therefore it loses mass. And its mass, it loses enough mass so that inside the nucleus it can no longer decay into a proton plus an electron plus a neutrino. So you're only here because of that accident that the neutron-proton mass difference is so small so that when a neutron is in a nucleus, it's suddenly stable. And that's why there can be heavy elements, the ones that are important for life, carbon, nitrogen, oxygen, iron, all those things, all those nuclei can only exist because this mass difference is so small that you put the neutrons in the nucleus and they're stable. A remarkable accident of existence. So the nature of that mass difference and the force associated with it is in one sense responsible for our existence. But of course this is also the force that's responsible for our existence in another way, and maybe the end of our existence, as the bulletin has focused on. It's the force that's responsible for the nuclear reactions that power the sun. The thermonuclear reactions that turn hydrogen into helium and produce all the energy that allows life to exist on Earth, but also, of course, produces the energy that produces thermonuclear weapons. So this may be a weak force, but it is one that is incredibly important for our history, our past, and maybe our future, if we have a future. So we need to understand it. So the first person to write down a description, a potential description of that force, is one of my favorite physicists from the 20th century, Enrico Fermi, from the University of Chicago. And Fermi was an amazing physicist. I could go on about him for a long time. He's a hero of mine and many others. He was the last physicist, nuclear physicist and particle physicist, who was equally good at experiment and theory. Now the two fields both have enough baggage that you're either a theorist like me or an experimentalist. But he could do both. And he, of course, as I was just watching at the Bulletin exhibit at the Museum of Science and Industry, which is an amazing exhibit, which if you haven't seen, you should see. Fermi built the first nuclear reactor as part of the Manhattan Project at the University of Chicago. And I've always thought it was great. It was underneath a football field, which I thought was brilliant, because if anything went wrong, you just kill football players, and it's no problem, no loss. So, but anyway, nothing went wrong, and they built that. But Fermi developed a model for this interaction, and he submitted it to the journal Nature, and it was rejected, which is a great solace to many of us who have been rejected by Nature many, many times. But Fermi didn't take it lightly. He was so disgusted that he said, forget it, I'm not doing theory anymore. I'm going to go do experiments, which was good for him, because the next experiments he did won him the Nobel Prize in physics, and were relevant, actually, the processes that were relevant for producing the bomb, it turned out. But so Fermi had this model, but others tried to develop it. Now, one of the important aspects of physics that we don't talk about enough is that physics is like Hollywood. If it works, you copy it. Okay? You keep copying it until Halloween 23. Okay, as long as it takes. And physics is the same. If it works, copy it. So if we've got the best theory in nature, this one, copy it. We have the best theory. This is quantum electrodynamics. The best picture gives the best predictions of any theory. Let's try and have a mimic that and produce a theory of this new force in nature. So we can draw a picture that looks the same, sort of. We have a neutron turning into a proton. It's made of quarks, but that's just an added complication. And then there's an electron neutrino emitted. And we can try and make a picture that looks the same by the exchange of a particle. This force works by the exchange of a particle. Let's make this force work by the exchange of some new hypothetical particle. But there's a problem. This force is long range. This force only works within the size of the nucleus. This one's much stronger than this one, apparently. So although it looks the same, they're very different. How can we accommodate that? Well, one way is simple. If we give this particle a big mass, then we can solve the problem. Because you see, the electromagnetic force is long range because the photon is massless. If we give this particle a really big mass, then because E equals mc squared, when you emit that particle, you emit a lot of energy. But the Heisenberg uncertainty principle says if you emit a lot of energy, then that particle has to disappear really quickly. Otherwise, you'd notice it. So if it's very massive, it can't travel very far, only the length of a nucleus or less. So you can explain a short-range force if you give that particle a really big mass. Great. Everything seems to work out. There's a problem, however. That is that this description is beautiful. This one's nonsense on the surface. This one produces beautiful predictions. This one produces infinities. Physicists don't like infinities. Mathematicians love infinities, but physicists don't, because when you have infinite results, you can't make any predictions easily. So this was actually remarkable, because this was a problem that was known in the 1960s, and it represents one of the important aspects of the story that make it great, in my opinion, that the science supersedes the scientists. Another big secret is that scientists are human, and don't let anyone know that, but it's okay. And that means that they have prejudices and biases, and they're pig-headed, and they'll go in the wrong direction, and they won't give up their ideas even if they're wrong for a long time. But the science overcomes that. The process of science, of skeptical inquiry, reliance on empirical evidence, testing, retesting, going back and checking, trying to prove yourself wrong, that forces the scientists inevitably in the right direction. And this was an example. When I was writing the book, and maybe if you read it, I wanted to shake these scientists in the 1960s and say, you're going in the wrong direction. The right answer is right here. Because in the 1960s, they were willing to give up this beautiful picture of relativity and quantum mechanics and said, maybe it doesn't work on the scale of nuclei. Maybe something new has to begin. They just gave up this wholeheartedly. But they didn't have to. But again, they were just fixated in the wrong direction. The right direction was somewhere else, and they should have realized it. The right direction comes from another area of physics, superconductivity. In 1911, this physicist named Kamerlingh Onnes, a Dutch physicist, discovered that if you cool mercury down to 4 degrees above absolute zero, it becomes superconducting, as he said. What that meant is that the electrical resistance goes to zero. To zero, not very small, but to zero. Now that may not sound astounding, but it should. Because that means if I take a mercury wire and I attach it to a battery and start a current going in it, and I cool it down to 4 degrees above absolute zero, and I take the battery away, the current continues. And it won't continue just for a day, or a week, or a month, or a year. It'll continue forever. It'll never stop. It's magic, it sounds like, because that kind of thing shouldn't happen. But the current will go on forever. He called it superconductivity. He had a flair for names. But it's a really complicated phenomenon. It took almost 50 years for physicists to derive a theory of how the interactions of electrons in the medium caused that, allowed that to happen. Okay, what's that got to do with anything I just said? Well, now we can make superconductors that are superconducting at a much higher temperature, so we can do experiments in high school physics classes that look neat. And here's one. We can make superconductors that are superconducting at dry ice temperatures now. And if we embed a superconductor in dry ice, okay, to make it superconducting, then if you take a magnet near it, and put the magnet on top of it, it'll float. That's the little thing we do in high school physics classes. Why will it float? Because it turns out magnetic fields cannot permeate a superconductor. They die off at the surface. And the same would happen for an electric charge here. It would float as well, because the electric fields can't die off at the surface. So what it means is the field lines, the magnetic field lines, get repelled, if you wish, by the superconductor, and that levitates the magnet. It's a fun little thing to do in a physics class. But now what's that got to do with anything? Well, now I want you to do what I asked you to do with the crystal. Imagine that you live inside this superconductor. What would you see? Well, you develop laws of physics. You develop quantum mechanics, and you try and understand electricity and magnetism. But for you, electricity and magnetism would be short-range forces. Because in the superconductor, the magnetic fields die off in a very short distance, as do electric fields. So the electromagnetic force would be very short range. If you developed a quantum theory to describe that, you'd have to have a particle transmitted that's very heavy. And in fact, inside superconductors, photons are heavy. Photons have a mass inside a superconductor. They're massless out here in the real world. They travel at the speed of light, but in a superconductor, they travel more slowly and they have a mass. Now, this should have been the key that people realized, but they didn't because they were looking in the wrong direction. And the key is basically, I like to think of it this way. Say you're swimming. You're in a swimming pool. You feel nice and light. You're swimming very fast. But if I replace the water with molasses and ask you to swim, well, most of you wouldn't do it, but some of you might. And if you started to swim in the molasses, you'd swim much slower. You'd feel much heavier because of the resistance of the molasses. Now let's imagine for a moment that there's an invisible field everywhere in the universe, everywhere throughout the universe in nature. And some particles, when they're moving through that space, they interact with that field and feel a resistance. And they might be massless, but they feel a resistance and they slow down. Just like the photons traveling in a superconductor experience a resistance and slow down and get massive. So let's imagine that if you wish, we kind of live in a cosmic superconductor, an invisible superconductor everywhere in the universe. A remarkable and absurd claim. But what would it imply? Well, we could now draw these two forces. I tilted it. The old one was sideways. The electromagnetic interaction was sideways, and so were these. But now here's a picture of that nuclear force with the quarks producing electrons and neutrinos. And it turns out there are 3 particles associated with the weak interaction, but that doesn't matter. But I now can draw them to look very similar. But now, let me imagine that these particles aren't massive. The ones that mediate the weak force. They're massless, just like the photon. But let's imagine that those particles interact with that background field and act like they're massive. And to us, they act like they're massive, and the force they mediate becomes short range. In that case, it solves everything. Because now these particles are massless at a fundamental scale. They only appear massive because of this accident that we live in this cosmic superconductor. And if they're massless, then the mathematics of this kind of, associated with these kind of diagrams, is the same as the mathematics associated with electromagnetism. So instead of producing nonsense, infinities, you produce numbers that you can calculate, and they're right. And better still, if the mathematics looks identical, maybe it's more than that. Maybe the forces are identical. Maybe the weak force, which seems so different than electromagnetism, both of which in different ways are responsible for our existence because of their difference. But maybe, in spite of the fact that they look incredibly different, they're really the same thing. The weak force and electromagnetism are really fundamentally a single force, which we now call the electroweak force. This would be a remarkable unification, the greatest unification of physics in the 20th century, certainly. One that's unheralded, in fact. Because it would mean that these two fundamental forces in nature are really the same thing, and everything we see is here by an accident. The fact that there's this invisible field everywhere in space. Well, that's the issue. Up to now, that sounds like religion. Think what I just said. There's an invisible field everywhere in the universe responsible for our existence. Okay, and if I left it there, it'd be religion. But it isn't, because this is physics. You can't assert the existence of an invisible field if you can't detect it. So how can you detect that invisible field? Very simple. Cosmic sadomasochism. You spank the vacuum. And you spank it hard. What do I mean? Well, in the quantum world, for every field, there's an associated particle. And that means if there's this invisible field everywhere, if I dump enough energy in a single point, maybe I can kick real particles out. Let me call that field the Higgs field. If I figure out a way to dump enough energy in a single point, maybe I can kick out real particles. I'll call them Higgs particles. That would demonstrate the existence of that field. How do I do that? How do I dump enough energy in a single point? Simple. I build the most complicated machine humans have ever built. The Large Hadron Collider in Geneva. This accelerator, which if you fly to Geneva there, and many of you may have, there's the lake and there's the airport. There's a little spray up there. And when you come out of the airport in Geneva, you look out and you see beautiful countryside, Swiss countryside and French countryside. Underneath that countryside, however, is a tunnel, a 26-kilometer tunnel around. And what we do is we take protons and we accelerate them to 99.999998% the speed of light in this direction, and 99.9999998% the speed of light in this direction. And we collide them together in a few places in this tunnel. We try and focus them down and dump enough energy into empty space to maybe kick out real particles. These particles go around thousands of times every second. Here's the French-Swiss border right here, by the way. So they go across the border thousands of times every second without passports or anything, which Mr. Trump is going to change if he hears about it. And so we do that. Now, in this country, there is an anachronistic holiday which we celebrate called July 4th, which means something to people here but nothing to anyone else, as it should. But now it has a cosmic significance, because on July 4th, 2012, we reported at the Large Hadron Collider that 50 events have been discovered, 50 particles have been produced that walked like a Higgs and quacked like a Higgs, and so we thought they were Higgses. And in fact, in the intervening 5 years, we've been able to measure them more carefully and produced many more, and every property of these particles is identical to that which was expected if the Higgs particles were real. We discovered the Higgs, which meant we discovered that there's an invisible field everywhere in the universe, that we live in a cosmic superconductor. I mean, it's truly remarkable. I must say, I was certain the Higgs didn't exist. I had 3 papers in my drawer waiting for them not to discover it. But nature, as in many cases, nature unfortunately hasn't been wise enough to follow my advice. But this is truly one of the most amazing discoveries in the history of science, because it really means that in a real explicit way that everything we see is an illusion. The properties of the universe that seem like they're designed for us, that make stars and galaxies and planets and aliens and people and everything, the particles that make us up, the interactions we feel, are all an accident of the fact that this field exists. If it didn't exist, none of the properties of our universe would be there. Nothing we see would be there. Everything would disappear. This story is the greatest story ever told. It's because because the real universe, the story of the real universe is so much more interesting than stories people invent. And to me, the reason I want to celebrate this here and in the book, and I think in the context of the bulletin as well, is because to me it represents humanity at its best. And the bulletin was developed to warn of dangers in some sense that humans develop by technologies, but not to forget that science has provided us with the technologies that allow us to exist at the same time. But more than that, the real great asset of science is not the technologies, I would argue. In fact, it's almost unfortunate that, although it's fortunate that science produces technology, most of us wouldn't be alive here now if it weren't for that. But when I talk about these things, people say, well, it's great. Does it make a better toaster or a faster car or something like that? And the problem is we associate science with technology. And the real virtue of science, to me, is the same as the virtue of art and music and literature, which is to change our perspective of our place in the cosmos. The cultural benefit of science is what's so important. It makes being human worth being human. To ask those questions and to change our minds and to change our perspectives, that's called learning. That's called civilization. This is civilization at its best. And in that sense, I think of the Large Hadron Collider as very similar to it's the Gothic cathedral of the 21st century. The Gothic cathedrals were built over centuries by thousands of artisans. Beautiful structures with the most sophisticated technologies at the time, learning how to keep those roofs up and things. Those artisans came from dozens of countries speaking many different languages. The Large Hadron Collider was built by 10,000 physicists over 20 years from over 100 different countries, speaking dozens of languages, different religions, everything. But none of that matters. They all came together to work towards this common goal, and the goal was not to develop a faster car. It was just to answer the question, why are we here? To learn something more about ourselves. The fact that we would spend 50 years amassing this and building the most complicated tools we can ever build just to answer this question amazes me. It's wonderful. And we should celebrate it because of what it's caused us to discover about ourselves, not because the World Wide Web was discovered at the Large Hadron Collider, or at least at the CERN before the Large Hadron Collider. So of course there have been benefits from it. But these machines are amazing. This is not the accelerator. This is just one detector. The Atlas detector, one of the larger ones. There's a smaller one called the compact muon solenoid, which isn't so compact. It contains, there's as much metal as there is in the Eiffel Tower in this detector. And you really can't, you feel like Gulliver when you're in there. And it's hard to appreciate it unless you're there. I have a better picture of it because I'm in it. But it's really it's amazing. And you can't give enough hyperbole about the Large Hadron Collider. Here's one fact. Every second at the Large Hadron Collider, enough data is generated to fill more than 1,001 terabyte hard drives. More than the information in all the world's libraries, every second. And the tunnel, the 26-kilometer long tunnel, has to be evacuated with a vacuum sparser than the vacuum outside the International Space Station. Every aspect of this gargantuan machine, brought together by people from all around the world, is amazing. And science brings people together. Science can bring people together. Science should bring people together. Another thing which I think in many ways is implicit in the celebration that the Bulletin is all about. The Bulletin is basically saying we want to preserve the wonder that's humanity, the civilization, the knowledge, the fact that we can live together. Science can be the basis of that. By using the tools that we've developed in science to uncover this illusion of reality, if we use those tools, we can uncover the illusions of reality in the political arena. Those same tools of skeptical inquiry, demanding empirical evidence for claims, testing things, looking at many different sources, not just echo chambers. All of these tools are an essential part of our existence, I think. And the best part of this is, and the best part of the title of my book is the so far. The greatest story ever told so far. Because the greatest part of this greatest story, the story of the real universe, is that it changes. It's not like that other greatest story ever told, okay? Which I heard referred to the other day as a way that I cannot help but use from now on as the goat herder's guide to the universe. But in any case, anyway, this story changes. It gets better every day because we discover new things every day because the imagination of nature is greater than our imagination. I happen to love art, and there's the Institute of Art nearby here, and I love art. My favorite area of art is the Impressionists. Because the reason I like Impressionist paintings is because they look really beautiful when you're far away, but when you get really close up, they're crappy. And that's physics. Because sure, we have discovered this standard model, the best theory in nature that describes every experiment we can perform. But every time you make discoveries, there are new questions, a host of new questions. Sure, the Higgs field exists, but why does it exist? Why did it freeze in the early universe in the way it did? Why didn't it freeze in a different direction? Why did it freeze at the scale it did so the weak interaction has the strength it does? All these questions we don't have the answers to. And the Large Hadron Collider is going to continue to operate for another 20 years to try and answer them. Maybe it won't. Maybe another machine will. Maybe we'll learn evidence from the early universe to try and discover it. The story gets better all the time. And this story will only keep on getting better if we keep on asking questions. And that's really what I kind of want to sort of end on. This fact that we should be willing to go wherever the universe takes us and go with our eyes open. Many people think of, when I talk to them about the bulletin, for example, think of it as a kind of a downer at times. The doomsday clock is a downer. Why would they think that? But as you know, as I think I said when we unveiled it this year, as Pasteur once said, fortune favors the prepared mind. And if you're not willing to go into the future with your eyes wide open, wherever it takes you, then you'll never be able to deal with the challenges of this century and the next century. And that's what the bulletin's all about, helping people keep their eyes wide open and not being afraid. And realizing that it's okay. For example, one of the discovery that I just told you about tells us that our existence is a cosmic accident. It is literally identical to this icicle again, ice crystal. Remember, that direction was really significant to these people, you'd think. But everything about the universe that seems like it's designed for us is really significant. People think the universe is designed for us because we live so well in it. Actually, we're fine-tuned for the universe, not the other way around. But there's nothing special about the fact that electromagnetism is long range and the weak force is short range. It's an accident. If the Higgs field had frozen in a different way, those forces would be different. We wouldn't be around to ask the question. Now imagine that the physicists on this ice crystal discovered that that direction wasn't very special, that there could be other ice crystals in different directions. Let's say they discovered that at 4 in the morning, when these things often happen. And at 6 in the morning, the sun rises, and it melts. Okay, and they're gone. The civilization is gone, and because they can only live on the ice crystal. Well, that too may be our universe. Because now that we've discovered the Higgs field and we do calculations, which we can't do completely because we still don't know why the Higgs field is the way it is. But when we do the estimates, we find out that the Higgs field is precariously close to melting. That the parameters of the Higgs field are such that it could go away. It probably won't, but it could. Now, I see nervous faces here. But you don't have to worry, because it turns out when we do the calculations, if it melts, it's not going to melt next year or a year from now or a million years or a billion years or a billion years. It will happen in the far future if it happens at all. But if it does, everything we see in the universe will disappear. All the stars, the galaxies, the planets, the people, everything will go away because particles become massless again. The universe will revert to a beautiful symmetric form, but not one in which life like us can exist. Which is another aspect of our misconceptions about the universe and nature, that somehow we're the pinnacle of everything and it's always going to be the same. Again, to relate it to the bulletin, one of the problems that I encounter, and many of my colleagues on the board encounter, is complacency about nuclear weapons. Since the Second World War, there's never been a nuclear weapon used, so why worry about it? Okay? Things change, and this too can pass. And our universe may pass, and so that's the way it is. The future may be unbelievably miserable. It certainly doesn't seem like it's designed for us, and I want to end with that design issue, because the illusion of design is really important in science. We are hardwired to look for purpose to things and to look for design. And so we look at Christmas ornaments and we say they're clearly designed by people to be artistic and beautiful. But of course, those aren't Christmas ornaments, those are snowflakes. Electron micrographs of snowflakes. So all you need is polar molecule in laws of chemistry and physics, and you make snowflakes. So there's no design there, even though it looks like it. But you say, well, maybe, but Chicago's famous for its architecture. So human architecture is clearly designed. Take good old Buckminster Fuller domes, which when I was growing up, all the hippies had them in their backyard. They did neat things in them. And clearly evidence of an intelligence. But of course, you can take Buckminster fullerene. Soot. If you take soot, you'll find carbon-60. Okay? And it's called Buckminster fullerene. It's a Buckminster fullerene. There's nothing less designed than soot. In fact, one of the chemists who discovered this was on our board of sponsors, won the Nobel Prize for it. So we have to be very careful when we think things are designed for us. And there's a long history of that. And of course, in my opinion, one of the greatest scientists that ever lived, greater than Einstein in my opinion, is Charles Darwin, who was the first one to point out that the illusion of design can be compelling, in this case, in life. And the last paragraph of The Origin of Species is one of the most beautiful paragraphs anywhere in the history of science writing, in my opinion. There is grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. The remarkable statement that the diversity of life on Earth and its complexity and the fact that it seemed to be so well designed for its environment could result naturally from the process of natural selection, without design, without planning, without purpose. And that changed everything. And really, that's what we're done in physics. We're saying that the incredible diversity of the laws of nature that we measure, that have produced all the structures we see in their incredible diversity, are not designed. That diversity can result from a very simple beginning. And accidents of nature, like the accidents of natural selection, can change the future. But we also realize that scientists are products of their time and myopic. And so in 1863, he said to Joseph Hooker, "It's mere rubbish thinking at present of the origin of life. One might as well think of the origin of matter," which was rubbish in 1863, but now I get paid to do it. Okay? And that's what's important, because what seems like rubbish to us now will not be rubbish 100 years from now, because science changes. The greatest story ever told gets better. And things that we cannot imagine science discussing or describing, that people will often say, "Oh, science will never describe this." I'm always amazed when someone says, "Science will never, ever explain X." Because think of the incredible conceit in that statement. Because it implies that somehow you know. If you know what science can't discuss, then somehow you must know something about it that we don't. We don't know what we'll understand unless we keep trying. Unless we keep willing to bravely go where no one has gone before, in that sense. To bravely go where the universe takes us. To continue the process of science. But not just science. Art, music, literature. To me, that's the tragedy of what we're living in right now that we have to fight as well. Not just a tragedy of ignorance associated with nuclear weapons. Unwillingness to recognize that climate change is happening. An unwillingness to worry about other problems that the Bolton worries about, from cyber terrorism to biotechnology, that we have to think about, that can produce wonders for humanity, but also potential terrors. And to me, the field of physics that I'm talking about is in the current, for example, in the current budget, proposed budget, is being cut by 20%. But that's not what's important. That's part of the Department of Energy. And what many people don't realize, including the current head of the Department of Energy until he became head of the Department of Energy, is that it is the major funder of all physical science in the country. It is the dominant funder of all physical science in the country, Department of Energy. Cut by 20%. But in that budget, as you know, there are other cuts. National Endowment of the Humanities cut to zero. National Endowment of the Arts cut to zero. Corporation of Public Broadcasting cut to zero. Institute of Museums and Libraries cut to zero. If you add all that up, the budget savings is $1.82 billion. I did the addition. Big numbers are easy for me. But if you look at that same budget, there's a line item of $2 billion, which is the first installment with a wall against Mexico, right? So we're willing, against to protect us from imaginary hordes, we're willing to get rid of the very essence of what truly makes this country great. And the greatest comeback to this I know of, and I want to end with, is from Robert Wilson, who was the first director of the Fermi National Accelerator Laboratory, which is near Chicago, which was, until the Large Hadron Collider was built, the largest accelerator in the world. And Wilson was asked in the 1960s, when it was being constructed, if it would aid in the defense of the nation. And here's the statement that he made. "No, sir, I don't believe so. It has only to do with the respect with which we regard one another, the dignity of men, our love of culture. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things we really venerate in our country and are patriotic about. It has nothing to do directly with defending our country, except to make it worth defending. And that's what we have to make sure of. The greatest story, the greatest gift that science can provide us will not continue if we step back and stop being willing to ask questions. And that's not just the greatest gift that science gives us, but art, music, literature, all the things that we really care about, that really matter, that really would make this country great. We don't, in 100, 200 years, it won't matter how many arms we sell to Saudi Arabia. It'll matter the literature, the music, the science, the things we produce that are called civilization. And so I'll end with two quotes. One from the beginning of my book, which was from Virgil, the very beginning of the Aeneid. I learned in Latin because I grew up in Canada, so I was educated. These are the tears of things, and the stuff of our mortality cuts us to the heart. Well, that's the famous quote, but at the end of the book I was looking at it again, and I was reminded of the next line in the Aeneid, which is much less well known, but to me equally important. Release your fear. And that's what we have to do. We have to release our fear of the unknown, of the threatening possibilities of civilization, of the future, which can be terrifying and wonderful at the same time, and boldly go and be willing to accept a future that may be miserable, a future in which humanity isn't the center of the universe, a future in which there are technologies that we may have to control, or that may change what it means to be human. And accept that with open eyes. And therefore, instead of being afraid, we should enjoy our brief moment in the sun. Thank you.
Thank you, Lawrence. We do have time for some questions, and we have a mic up there and a mic down here.
There's a mic up there too.
And
okay.
so if you do have questions, please go ahead and raise your hand. Wait for me to recognize you, and then ask your question into the mic. And please keep it brief, only because there's so many of us here. Anyone?
Yeah, we'll go for a few minutes, and then I'll answer questions later out there. Here's one.
So right here, please.
You argue for a universe based on happenstance, and how
I don't know whether I argue about it. I just say that's the way it is. But
okay, and if you accept that, then do you think that it's just a human construct that we seek symmetry and beauty, and is that a legitimate pursuit?
Well, humans seek symmetry and beauty, and so do scientists, because scientists are human. But we have to be aware that just because something appeals to us doesn't mean it's true. And that's really important in physics. We have to be aware that just because something's elegant or what appears to be mathematically beautiful to us, that doesn't mean it describes the universe. Nature is the ultimate arbiter of what is true. And what also works out after the fact, almost always after the fact, I have to admit, we can see the beauty of things after the fact. Maxwell's equations, when he wrote them down, were not beautiful in any sense. And the description, the wheels within wheels, if you read his papers, there's anything but beautiful. But now we have these 4 beautiful equations. And then underneath, physics students wear them, and underneath it says, let there be light. Because that really explains why there's light, not like the other argument. Okay? And so I think we have to realize that humans, of course, are hardwired by evolution for many things. And what we call beautiful is, in fact, what we call beautiful is also culturally determined. What you think is beautiful is very different than people from other cultures. Science takes us out of that myopia to realize that what we think is normal, beautiful, wonderful, or the way the world is supposed to be may not be the way the world's supposed to be. And that's what's great. I once said, and I think I may even say in the book, that one of the purposes of science is to make you uncomfortable. But it's the purpose of it's the purpose of learning. Because if you're not at all uncomfortable at the beginning, then you're not ever going outside your comfort zone. So be wary of the fact that we want to believe, as the X-Files would say.
We have a question right up there.
Yeah, hi. I have a softball question for you.
Mm-hmm.
A study that I've noticed one of the most fundamental churches has done, they started it in 2009, and their words, just about every denominational church in North America is hemorrhaging young adults. I wondered, with your travel and as a professor, do you notice that kind of trend of them leaving, or actually, as in your perspective, joining more people taking science, and they noted that the trend
wish more-
happens
Look,
after grad school.
Yeah, look, there's a hard... as a professor, I'm very worried of how little historical perspective I have. Because I remember, it is time invariant that my colleagues who are older than me will always tell me that students were better. And I say that to my younger colleagues when I see students, because we have memories of things. So I'm very wary of anecdotal evidence that I might have. It is certainly true, however, that in the first world, there's a monotonic decline in the number of people who declare themselves of having religious, any religion. And I think that is a property of, in my opinion, of education, of the educational system we get. But at the same time, what is really much more of concern to me than that doesn't, either way, that doesn't bother me. What's more, I'm more concerned about people accepting the real world. I don't care what other things I think. And being willing to deal with it when it comes to public policy. And what is sad is that everyone is fascinated by science, even if they don't know they are. And every time I run an event in Arizona, we have 3,000 people come to it. People are they're just fascinated by science. They just don't know what science they're fascinated by. Because we teach, among many reasons, we teach science the wrong way. We teach science as a collection of facts. But that is exactly wrong. Science is a process for discovering facts. And we don't teach the process. The process is something that everyone innately enjoys, because everyone loves solving puzzles. But if you just teach science as a bunch of facts, then people can have alternative facts. Okay, and we're seeing that. But what we need to do is teach that process of using science. And by science, I just simply mean empirical evidence combined with reason and logic, basically. Those things together. And that I see no evidence happening in the public arena, which is why it's necessary for groups of scientists and others to, like the Bulletin, to speak out when people don't accept empirical reality for empirical reality. And I think the only solution is not a direct political one, but the solution, in my opinion, for democracy is to train young people in schools. I mean, when I was growing up, schools were depositories of information. But there's more information in this than I got in school, but there's more misinformation. What we have to teach kids about is the way to tell the difference. And the way to tell the difference is ultimately the scientific enterprise. And for a healthy democracy, an informed electorate, there's a wonderful quote in the Bulletin exhibit in the museum about just that ultimately, for an informed democracy, we need to have an informed citizenship, people who can tell the difference between sense and nonsense, and then can demand our legislators to do so at the same time. So, sure. There's
there was a
one
question.
there and then one there. Yeah, we'll go back and then we'll come up front and then maybe we'll quit.
Here.
Yeah, or how about the woman first? Oh, you're moderating.
Go
you
ahead.
choose.
No,
Sorry.
you're in charge.
I see. Okay.
Yes, please. I didn't
Okay.
see you. Go ahead.
That leads to the question: if human beings are hardwired to learn and be convinced via story, via narrative, don't we need to have more scientists who will embrace that fact of transmission? It seems like there's often a disparity there, or a disparagement, actually, of story for information, and we've got to find a way to embrace that part of the way humans learn.
Well, I think we'd have to. I think really the way the story, more fundamental than stories, and I do think we need to tell stories, and that's one of the reasons why I tell stories. But it's more than that. I think what really gets a story going. There's a great quote from one of my books that I wish maybe someone has here, but it says that the most important part of any mystery is how did the traveler get to the starting point in the first place. And really what we want to get is people to the starting point, and that involves questions. So really what gets stories going is questions. What could happen if? What might happen? How could this happen? And in my opinion, we should teach using questions rather than answers. The answers aren't important. As a physicist, 99% of what I know I learned after my PhD. Okay, the information, it's the questions, and kids love puzzles, and teachers and parents and politicians should all be willing to say when a kid asks a question, I don't know. I don't know. Let's find out. Or maybe we don't know. Maybe we should think about it. And so I really think that's the basis of good storytelling, is ultimately raising questions and getting kids to ask the questions, and then make it a process of discovery, which is also part of storytelling. It's not being told who killed them. It's the process of discovery, of reading the story and discovering for yourself what happened. Anyway, that's my... Now, this
Let's
gentleman
go
we
here, because you've been
bypassed
very
earlier.
patient, and then we'll come down.
Yeah.
Yeah.
So I have a bit of an awkward question, or a strange one, I guess, but I'll throw it at you in hopes you might entertain me.
Okay, sure.
So I've always been interested in science and physics, and a few years ago I really started to get curious about science and physics and how it applies to things like consciousness and life and what happens after death and things of that nature. And I'm wondering, is there anything that about that topic that you might be willing to share with us?
Sure. Yeah, which is literally almost nothing. People think I'm joking when I tell them that I do physics because it's easy. But it is. Consciousness is a lot harder. We don't know what... there's not even a good definition of consciousness, in my opinion. I run meetings on consciousness, so at my institute, which looks at everything and well beyond physics. And so it's just much harder. And so physics deals with the low-hanging fruit. That's why it's been so successful. Consciousness is a topic which I think and the brain is an area of hot understanding for which there are new techniques to discover and learn about, because science progresses really when there are new experimental techniques. But we're at the infant stages of that. And when anyone tells you they understand consciousness in general, I think you should just walk away. Certainly, as someone pointed out to me, you can tell how well we understand something by how many books are written on it. The more books, the less we understand. That's right. Because, quantum mechanics, you just have a book on quantum mechanics. You don't need 100. There are a number of books, but one book will do. Dirac's book on quantum mechanics is all you need. Okay? And there are tons of books on consciousness because we don't understand it yet. So physicists really have nothing to say about consciousness. And there are some physicists who claim to. But we should be really skeptical of those, just like you should be skeptical of everything you read. But it's going to be a long way. But now when people say, we'll never understand consciousness, that's garbage. Because, we're learning a lot. And probably one of the ways we'll learn about consciousness, and the Bolton is going to be involved and has been involved in a meeting we've run on artificial intelligence at my institute, and one we're going to run, probably we'll learn about consciousness by understanding machine consciousness as we make machines that one day may be conscious. So I think that'll be interesting.
There's a question right here.
I've listened to your episode on the Joe Rogan Experience about 4 times now, and I'm still struggling so much to understand, the content. So I'm sure I'll do just fine with your book. But my question is, what advice do you have for someone like me who's trying to continue to ask these questions and continue to inquire and really not, adopt one certain ideology or one certain form of thinking, but just to continue to do research and ask these questions?
Well, continue to ask questions. Really continue to ask what interests you. That's all that matters. I only do what I do because it interests me. I hesitate to give advice, but I'll give you I often get asked by students what advice in their new physics students, and I always tell them the same thing. Don't let the bastards get you down. Namely, always remember why you're interested in stuff, and just keep asking questions. And you know what? You don't have to master things. That's the other misconception about science that bothers me so much. That people somehow think that if you're not a scientist, you can't, it's not even worth reading. Forget a book like mine or anyone else's. And it amazes me because, again, you don't have to be Eric Clapton to enjoy the guitar. You don't have to be Picasso to enjoy paintings. You don't have to be Shakespeare to enjoy plays. But somehow people think you have to be a scientist to enjoy science. And that's not true, because it's an experience all of us can share. So just keep reading and asking questions and following your interests. And the world is a wonderful place, and you don't need to be a master of everything or a master indeed of anything to appreciate the vast wonder of the universe. Just enjoy it.
We have time for one last question.
That was a good way to end, but we'll take another
Yeah, we'll
one.
take one more, though.
No, so this question, which had
Yeah.
better be a really good question.
Yeah.
I guess my question is, when you talked about the Higgs field and how the specific, settings of these numbers, the cosmological constant and everything, constants, relate to our existence, do you feel like that's all there is and we happen to just have that lucky roll of the dice? Or is there some sense that you have that all these things have or do exist in some sort of multiverse and we're just on the one that we can exist on?
Well, we don't know the answer to that question. But it could be that you're right. It could just be that the Higgs field froze in our universe in the way it did. And it could be that other universes exist in which Higgs-like field froze in different ways, and then the laws of physics would be very different. In fact, that's the best motivated picture we have now based on some other fundamental physics that I describe in another book, In the Universe from Nothing. It's most likely we think there are other universes, and it's quite likely the laws of physics are different in each of them. In that case, then you can understand this picture that I just gave you in a way that really is very similar to that of Charles Darwin. Because what I would describe to you that is cosmic natural selection. You know, bees weren't designed to see the colors of flowers. They wouldn't exist if they couldn't see them. We would be amazed to find ourselves living in a universe in which we couldn't exist. It would be worth a book or two, but no one would read it. And so it really could just be that the properties of the universe that seem so fine-tuned for us, or rather that we are fine-tuned for, are just that, are just an accident in that sense. Or it could be that even in what you might call a single universe, the Higgs field could, over what are called causally disconnected regions, could freeze in different ways, and once again have different laws. It's very different than when I was growing up. When I was growing up, I wanted to be a scientist because I wanted to describe why the universe is the way it is. It's very disconcerting to think that in general, the universe is quite different than it is us, and it's a cosmic accident. But once again, the universe doesn't give a damn what we like or not. And so the current best picture is that maybe there may be no fundamental reason why the Higgs had to freeze in a way it did. That in different universes it'll freeze in different ways. And that's probably the best picture, which I find immensely satisfying because it's, again, like that ice crystal. There are many ice crystals in that image I showed you. There are probably many universes. And, you know, it doesn't mean that life can't exist in those universes. It just means that life like ours can't. We don't know what the locus of all possible intelligent life forms is. So it could be that with different laws, different systems can exist. And those beings in that other universe may say, wow, isn't it amazing that the universe is just so fine-tuned can exist? It's just like, to me, it's just like asking, isn't it amazing that my legs reach all the way exactly to the ground? Thank you.